thank you everyone for inviting me for this talk today, and let me talk about one of my favorite topics, which is optimization. Before I get started, let me quickly introduce myself. My name is Andrea. I'm an optimiser at Satalia already for almost 5 years, and I got my PhD in computer science in an area of optimization, and I've been solving optimization problems for around 14 years. I live and work in Vienna, and as you can see on the picture, I'm a bit of a bike nerd and really enjoy hanging out with my mountain bike in the woods. Okay, so what am I going to talk about today? I'm going to cover mostly 4 topics. So the first is, what are optimization problems? Why are they hard to solve? How can we solve these problems? And I'm going to give an example about optimization in a hospital environment. So if we talk about optimization, I think it's good to first consider the process of how optimization works. So the first step when tackling optimization problems is to truly understand the problem we want to solve, to understand the optimization problem. After we have a good sense of the problem and have fleshed it out, we typically create what we call a mathematical model. The mathematical model is a kind of formalism to describe in mathematical terms what we want to solve. And once we have this model, we typically create a solving algorithm based on that model. And this is often a circular process. So what often happens is we create a solving algorithm, we create a solution, then we show the solution to whoever wants the problem to be solved, and then we might reiterate, we might not have understood all of the aspects of the problem, and so then we then adapt our mathematical model, and then we adapt our solving algorithm. So we are going to start also this talk at the first part, understanding the problem. And as I said before, we're going to look at a problem, an optimization problem that arises in the hospital environment. So the example I've picked is about operating theater scheduling. And the example is looking at children who have lung and heart problems. So these problems can be chronic problems, they can be acute problems, and to get treatment for these issues that these children have, they have to go to a hospital. In the hospital, they would get a treatment typically through an operation. Operations that are performed by specific medical staff, mainly surgeons and anesthetists. And after the operation, the patients typically have to stay at the hospital for a certain time to heal from the operation. And there are different types of the hospital ward, of where these patients would stay to heal. And typically there are 3 different ones. So the first one is the hospital ward. This is the normal ward for patients who are not very vulnerable, where they don't need specific care. The second level would be the intensive care unit, or ICU, where you would typically have one single nurse attending to each patient. And finally, we would have isolation beds for the most vulnerable group of patients who need to be isolated to make sure that they don't catch any germs or anything else like this. So this is typically necessary after a heart transplantation, for instance, when the patient then is extremely vulnerable and needs to be in an isolation bed for a given number of time. So this is the whole process of how a patient would be taken care of at the hospital. And to decide which patient is going to be treated at what time and to what ward they're going to be assigned to, we typically have someone or some system that performs the operator theater scheduling. So they have to decide which patient is going to be treated when, by whom, and they also have to make sure that if a patient is treated, that the respective bed is available for the patient. So unfortunately, we have some uncertainties when we look at operator theater scheduling. So on one hand, we do not know how many patients are going to be coming in and which patients are going to need some treatment. So a certain percentage will have elective treatments, but there will also be some acute patients that will have to come and will need some treatment. On the other hand, we also don't know the recovery time because we cannot predict very well the outcome of the operation. So we can predict that a person might need to go to an isolation bed, but we cannot tell how long they're going to be in an isolation bed. In some cases, the operation might not be a very severe case, but the patient still might get into a worse condition and might need to go into intensive care. So these are the two uncertainties that make this whole scheduling problem even more difficult. And what we're going to look at is this optimization problem of how can we schedule the theaters and the wards so that we can treat as many patients as possible, and that we also don't violate any of those important constraints, such as that a bed has to be available for a patient when they receive their treatment. So we're going to look at what typically in the hospital, this would be a senior member of staff that would make these schedules, but that an optimization system could do instead of them. So what would be the actual outcome of this operator theater scheduling? It would be a schedule. So here is an example for the operation theater. We see here for each day, each block here represents an operation, and the coloring represents which surgeon is going to perform the operation. What we also need is a schedule for the ward. So here we see the schedule for each of the beds that are available. So we have 3 ICU beds, we have 3 ward beds, and we have 1 isolation bed. And each of those blocks here represent a patient that is planned to take the space in this bed. Now, as we said before, it's really important that when we schedule an operation here, we have to make sure that there is some space in the respective bed. So if this is a very long heart transplantation operation, we have to make sure that the isolation bed is available for exactly that patient. And what we also said is that we want to have a good solution, we want to have a good schedule. So this means we prefer 9 operations over a schedule with only 7 operations. So I hope that I've outlined quite well what this scheduling problem is. For the sake of simplicity, we're not going to look into the uncertainties that I've talked about before, but mainly just at the problem of how can we set up this scheduling problem. So how can you detect optimization problems in practice? How can you recognize them? They have some very specific features. So first of all, we have to make some decisions. And for each decision, there are typically many different choices. So in our case, we have to decide which patient are we going to operate, who is going to operate them, when are they going to be operated, and in what ward and in what bed are they going to be assigned to. And for each of those decisions, there are many different choices, and that will make the problem very difficult, as we will see later on. We also have constraints, and we have constraints because we typically have limited resources. So this means we have limited time, we have limited staff, we have limited ICU beds, etc. And we have to deal with those limited resources, and this adds constraints. So a sample constraint in our problem is that if our patient is treated with a heart transplantation operation, we need to have an isolation bed ready. Finally, we also have an objective, and the objective determines what makes a solution good. Typically, this means we want to minimize or we want to maximize something. So, for example, we want to maximize the number of treated patients in our example. We might also want to minimize the costs of running the hospital, but there are different types of objectives. So this is what determines an optimization problem. So we have understood the problem, so how can we now mathematically model these problems? So a mathematical model consists of different components, And I'm now going to go through those different components one by one for our our hospital optimization problem. The first thing we have are constants. And a constant is what we consider a feature that will not impact the number of decisions we have to make or the number of choices we have. So an example for constants in our problem are the length of an operation or the maximal working hours of a surgeon. They do not impact the number of decisions we have to make. Second, we have parameters, and parameters are now features that do affect the problem size. So they have a direct impact on the number of decisions or choices. So the number of surgeons, for instance, will make a big difference on how many choices we have for operating, the same as the number of patients. If we have more patients, we have to make more decisions, etc. So these parameters, the parameters are really vital for our problem model, and it's good to differentiate between the two of them. The third component of the mathematical model are decision variables. And the decision variables encode the decisions that we have to make and the choices that we have for them. So examples for the decisions we have to make is which surgeon is going to operate a specific patient, which ICU bed is going to be the bed for patient B after they have been operated, and etc. So if we dive a bit deeper, a variable is nothing but a mapping of the decision to the choices. So as an example, we would introduce a decision variable for the start time of a specific operation. And let's say we have 4 different options that we can choose from, then we would map this decision to those values. And we say we have made a decision, or if we assign a specific value to that decision. So this would happen during the solving process. But for now, we're just saying what are the possible choices for this decision. And if we dive a bit deeper, what we really do is that we encode those values by integer values, or maybe even by continuous values. And our variables are, for instance, in this case, we would probably represent it as an array of variables where 2 indicates it's the second operation. We also have different encodings of the decision. So another example of how to formulate the decision is as a yes-no variable. So we say we have a decision, the start time of operation A is going to be at 6 a.m. and we have 2 options, yes or no. Or the start time of operation A is going to be 7 a.m. We again have those 2 different options. And this is basically encoding the same decisions as we had with the other variable. It's just that the values are different. And in practice, we call them 0-1 variables because what we do is we assign them either the value 0 or the value 1. The question of how to formulate your decisions depends on your solving approach. So in some cases, you might be better off using 0-1 variables. In other cases, you're better off in formulating the question more with the integer variant that we've seen before. Okay, now let's move on to the constraints. We basically have 2 different types of constraints, and the first one are hard constraints. These are the constraints that have to be fulfilled, so they must not be violated. An example in our problem is, for instance, as we've already seen, patients can only have a heart transplant operation if an isolation bed is available. We also have constraints that we need to add just because it's a model that we're representing. So we say surgeons can only operate 1 patient at a time. Other constraints come from working regulations, such as surgeons may not work more than the 60 hours that are in the maximum due to the working regulations. How do we formulate hard constraints? Typically, this is done by expressing them through a formula. As an example, if we want to specify the constraint that operation Y cannot start before operation X has finished, we say that the start time of operation Y, so this is a decision variable, has to be greater or equal the start time of operation X, which is again a decision variable, plus the duration of X, which is probably going to be a constant. There are often several different ways of how we can formulate constraints, and it can make quite a difference of how you formulate them. But this again depends on how you actually solve your problem in the end. So we have hard constraints and we also have soft constraints. So soft constraints are those that can be violated, but if they're violated, there's going to be a penalty added to your you will have to pay a certain penalty because the solution quality is decreased if it's violated. So some examples for these are the surgeons should work less than 14 hours per day, or patients should wait less for 3 weeks for an elective operation, etc. And the soft constraints are formulated very similarly to hard constraints. We have some kind of formulas, but we also add some certain terms to the objective function. And the objective is the very last part of the mathematical model. And the objective tells us it defines how the quality of a solution is exactly defined. So it tells us what makes a solution good. And we usually do that by stating what we want, something we want to maximize or we want to minimize. So we might want to maximize the patient happiness or maximize the staff happiness or just minimizing the operation costs. And often we don't just have one objective. Often we want to do several things at the same time. And this is what we call to have multiple objectives. So in our example, we could, for instance, consider that we have 3 different objectives, A, B, and C. We want to maximize the number of operations. We want to maximize the staff happiness, and we want to maximize the patient happiness. Now we can formulate it in a way that we say we assign each of these objectives a certain value depending on how much we can fulfill this. And let's say this value can take a value between 0 and 100, where 100 is the best you can take. And let's say we have a solution where we assign 80 to the first part, 40 and 90 to the other twos. And we would then count all those parts together and we will get a certain value. And this would be what we call our objective value that determines how good our solution is. So for illustration, let's say we have 2 solutions. So the first solution we've seen before, and now we have another solution. Now these 2 solutions have the same objective value, but they differ quite significantly in what they do for the different objectives. So in the second solution, the staff happiness is increased, but we are serving fewer patients. And often what we want is we want to prioritize certain objectives over another objective. So we might want to say it's actually much more important that we have a high number of operations than, let's say, the patient happiness. So what we can do is we can add weights to the objective. In this example here, what we often do is we take, let's say we have 100% for the weights, and we give proportions of those 100% to each objective. And in this case, we say that objective A and C are weighted the same, and objective B slightly less. And if we now evaluate our 2 solutions, we unsurprisingly see that now the first solution is preferable because their values for A and C are higher than the ones for the second solution. Now, if you would change the weights for different priorities, we might say the staff happiness is the most important thing for us. Now those 2 solutions are going to be evaluated again differently, and now the second solution is preferable because it has a much higher value for the staff happiness. I should have also mentioned that if you have any questions or something is unclear, then please interrupt me and ask questions. Okay, so I hope this was clear. This is how we deal with having several objectives. It's generally a quite difficult task to find the weights that really match your priorities. It's often not clear, especially the more objectives you actually have, and it's also challenging from a solving approach point of view. Okay, so now we have formulated our mathematical model. What typically happens is that as soon as we model this problem, we perform some mathematical magic that I will come to later on, and then we receive a solution. And before we go to the maths magic, I want to have a quick look at the solution, what a solution means and what a solution is in the mathematical sense. So an example solution for our problem is an assignment of each decision value, a variable, to a value. So as an example, we say the surgeon for operation A is Dr. Chan, for operation B, it's Dr. Johnson, etc. And what is important is that we call a solution feasible if all the hard constraints have not been violated. So if they're, in this case, we cannot see exactly that those hard constraints are not violated because I only show a part of the solution, but let's just assume that these hard constraints are all fulfilled and this is good. And we also can look at the soft constraints. Let's say some soft constraints have been violated, but that's all right. And we get some objective value that tells us the quality of the solution. So now what we can do is we can also change the solution. Let's say we replace Dr. Johnson with Dr. Chen. And in this case, what can happen is that we violate a hard constraint. And in this case, our solution is what we call infeasible. So an assignment where we assign a value that breaks a constraint, that's what we call an infeasible solution. Okay, so we have now seen what a feasible solution is, what an infeasible solution is, and I think it's good if we now step back once and look at how many solutions do we actually have. So making some more general observations of solutions. So let's look at an example. Let's say we have two decisions we have to make and we have two choices. So we want to decide the start time of operation A and operation B, and we have two choices. So now my question to you is, how many solutions exist for that? Anybody dares? Okay, so the solution space, what we call the solutions we have are four possible solutions. So we can either say both are going to start at 6 a.m. We say one starts at 8, the other one at 6, one at 6, one at 8, or both at 8. So those are the possible combinations we have. The set of solutions we typically call the solution space in mathematical terms. Let's look at another example. So let's say we have 3 possible choices for our decisions. How many solutions exist now? Okay, so in this case, we have 9 possible solutions. So we have 9 combinations that are possible. Let's look at one more example. What happens if we have 4?
Is it 16? Is it
exactly.
Every time?
Exactly, 16. Can tell I'm talking with people with a software engineering background. They already know what's going on. Yeah, so we have 16 possible combinations. So if we look at the actual formula for this, the number of solutions is determined by the number of choices to the power of the number of decisions. So this is what we call there's some exponential growth. And if we look at some examples, you can see that this very quickly gets out of bounds. So if we have 10 decisions and 10 choices, we are already in 10 billion solutions. And for an example with 300 decisions and 20 choices, we are already looking at a massive number. And having to make 300 decisions with 20 different options or choices is not very uncommon. This is very common in industry, or typically you might even have to make thousands of decisions. So what we also have to bear in mind is, even if we had a computer that could calculate a solution extremely quickly, it would still take billions of years to compute all of those solutions. And even if we improve our systems by another, let's say 8 figures, it would still not make any significant difference. So it takes a very long time to compute all of those solutions. And this is a big problem. So to summarize this, the number of solutions increases exponentially with the number of decisions and choices. And for most practical problems, we just don't have the time to calculate them all. Okay, so I think we're ready now to start looking at how we're actually solving these kind of problems, because we've seen the mathematical model, we know what a solution is, and we know that there exist many, many different solutions. So before we look at the actual algorithms, I want to again look at the solution space. So remember, the solution space are all the solutions that exist for a problem. And let's assume that here we have the solutions to a specific problem. They're ordered in, let's say, some random manner. We don't know if there's any structure behind it. Now, typically, of course, this depends on the problem, the solutions will look a bit like this. So there will be some infeasible solutions, there will be some really bad solutions, and we will have maybe one or maybe several optimal solutions. So if we put some context to this again, a very bad solution means we only operate, let's say, 2 patients, and the optimal solution will, for instance, say we can operate 10 patients. This also means that there is no solution where we can operate 11 patients. So this is a kind of upper bound. An infeasible solution would be one, for instance, where we might be able to operate 20 patients, but there is no space in the ward, and this is why it's infeasible. So the problem is, however, that when we formulate the problem, we don't know anything about the solution. So this is just a black box, and we have to look at the solutions individually to actually infer anything about them. So let's say we look at one solution, we find out it's infeasible. Then let's look at another one, and this looks actually pretty good. Then we look at another one, and this is much better than the one we saw before, so this is actually much better. We find another one, and this one is even better. The problem here is that if we look at any solution, we can only tell how good it is when we compare it to the other solutions. So if you want to find the optimal solution, we have to prove that there exists no solution that is better than the one that we've seen. And this is quite problematic because, as you know from what we just talked about before, we don't have enough time to look at all of these solutions. So how do we manage to find optimal solutions then? How does optimization do it? And the answer, of course, is that optimization is magic. So I'm going to introduce you quickly to the 2 main lines of magic that we have in optimization. So the 2 main lines are, on one hand, exact algorithms, and on the other hand, heuristic algorithms. For each of those, there are many different solving paradigms, and I won't be able to go into detail with all of them, but what is important to remember at first of all is that the exact algorithms are the ones that are sophisticated and extremely clever, use a lot of mathematical concepts, and they are able to prove that a solution is optimal. The drawback with those approaches is that they can take extremely long to solve. So for many practical problems, they will probably not be able to find a solution, even though they are extremely clever. On the other hand, we have the heuristic algorithms, and these are approaches that are often simple or straightforward, and they also do not guarantee that you have an optimal solution. So they will give you a solution, but they won't be able to tell you how good it is. They can't even tell you if it's very good or if it's very bad. But the big advantage of them is that they're extremely fast, or often they're extremely fast, and can be very useful for problems in practice. So is there anyone here who knows why there is a raven with the exact algorithms and a badger with the heuristic algorithms? Okay, I guess there are no Harry Potter fans around, or they don't want to out themselves, but that's fine. Okay, so let's have a look at the exact algorithms, how they work. So the exact algorithms are the idea behind them is to structure the solution space in form of a tree. And when I say tree, I mean a tree the other way around. So the root is up here, and here are the leaves. And the whole idea of structuring it as a tree is that you can then perform some analysis on the tree. So you explore the tree in a dynamic and structured way. And then you analyze the tree at each node. And what you can do is you can often tell that a certain branch is not going to be promising. So you might be able to tell here that any solution that is in this branch of this tree is not going to contain the optimal solution. And what you can do then is you can simply cut off this branch, and then you continue exploring the smaller tree. So this way you can often cut off big parts of the solving space. And this is done by this very structured approach. So how can you cut off branches? There are several different approaches, several different ideas behind it. Here are some of them that are used in different solving paradigms. So the first one is called relaxation, and it's really called relaxations in the mathematical term. And the idea is that you just pretend that the problem is actually not that difficult, which means you're going to remove some constraints of your problem. You're going to remove those constraints that make the problem really hard, and then you're going to solve it. And this can be helpful to cut off branches or to make some analysis in the nodes. The second idea is that you simply learn from your mistakes. So a mistake is, for instance, if you iterate through your tree and you find an infeasible solution, it might help to understand how you got there and to try to not end up in a similar space again. And then you can also add some constraints and remove some parts of the tree. And this is also called no-good learning in some of the solving approaches. Another idea is that you simply add constraints as you go. So you become cleverer as you iterate through the tree. You might, for instance, find a solution where you can schedule 6 operations, and you can simply add a constraint where you say, I only want to find any solution is infeasible if it has less than 6 operations. So these are some ways that are used in exact algorithms to look close to cut down the search space and then to really pinpoint the optimal solution and prove that there is no other solution. Okay, now let's move on to the heuristic approach. So as I said before, the heuristics, they will find a solution, but they cannot tell you anything about the quality. And the key idea for their success is that they don't look at all of the solutions that exist. They only look at a subset, and they also try to look at the set of solutions in a structured way. The main idea is that you try to first come up to, or to start from one solution, and then you modify bits of the solution, and hopefully you're going to end up at better solutions by doing this in a specific way. So I'm going to present one such solving approach that is one of the most basic ones. It's called local search. And the idea is that you define something that's called an operator. And this operator changes an existing solution. It makes a small change, and then you have a new solution. And this new solution is typically called the neighboring solution. So an example for these operators could be that you might switch the surgeons that have been assigned in an operation. You might switch the patients. You might change the operation times, and you see what happens. So this means you might start from an initial solution. Then you apply 3 different changes. For instance, here you switch the surgeon from surgeon A to surgeon B, to surgeon C, to surgeon D. And how this typically works is you apply one operator, then you have 3 different solutions. Then you might pick the one that has the best objective value, so the one that has the best quality, and continue with that one. Let's say it has been this one. Now you make another change to the solution. Now you switch operating times. You again search for the best solution, and you again apply some other changes, such as switching another factor of the problem. So the advantages of this approach is that it's extremely easy, and it's also very fast. easy to implement. But the problem is you still stay in your neighborhood, so you won't be able to reach every part of the solution space. So this obviously also depends on the operators you add, but this is one of the big drawbacks. So the problem is you might stay in an area where the optimal solution is not there, or a good solution might not even be there. You might want to reach a very different area. So this is what we also call, you might get stuck in a local optima. So in a local good solution, but the better one is still somewhere out there. And what more sophisticated heuristics typically applies, they will apply some special measures to get you out of this local optima. For instance, by making a complete random change to the solution, and then you're somewhere else in the solution space. So if you're interested in any of these approaches, I would recommend to have a closer look into any of these different types of solving approaches. I cannot go into detail with all of them because probably each of them I could talk another 45 minutes about, and it's definitely worth it. Also, what I should say is, in practice, you don't go for either exact algorithm or heuristic algorithm. You often make a combination of them. So you're trying to combine the best of both worlds. And these hybrids are the most powerful ones, and also the ones that we use at Satalia, for instance. Okay, so we have been through the whole process now. We have had a problem, we've looked at the mathematical model, and we've also looked at the different solving approaches, so it's time to quickly wrap up. What I hope that you will remember from this talk is that optimization is about making decisions, and in particular about making good or ideally optimal decisions, that these problems are hard because there's so many possible solutions, and that optimization is really exciting and awesome. Okay, thank you very much. Do you have any questions?
Hello. Yeah, so do you have any recommendations as to libraries that are useful in solving these sorts of problems? In the past, I've used Google OR tools. Have you heard of that library? Or I think it's like a set of tools. Is there any other ones that you'd recommend that are worthwhile knowing about?
So I think OR tools is a very good library. They have a very big set of different solving approaches, and it's also open, and I think you can actually check out the code. So I think this is a very good library. Other libraries, it depends really on what kind of solving algorithm you want to use. So if you look into a mixed integer programming approach, which is quite common, the most powerful libraries are the commercial ones, but you also have very good open ones. So the question is, are you willing to invest into a commercial tool, or do you want an open tool?
Yeah, I guess it depends on the problem, doesn't it?
Yeah.
Yeah.
The benefit of working with an open tool is that you know exactly what you're doing. With some of the commercial tools, they're extremely powerful, but you have no idea what's going on in the background.
Yeah. Even more magic.
Yes,
yeah.
yes, that's true. Any more questions?
Sort of taking Paul's question a bit further, Andrea, what would be your sort of typical sort of tech setup and sort of tech stack you would work with?
So you mean what kind of solving approaches we often use?
Yeah, so in terms of language choice and technologies involved.
Yeah, so the language choice really depends on the client we're working with. And we often build combinations of heuristic approaches with exact approaches. Often we use something that's called large neighborhood search, which is a very, very powerful tool where you can use an exact approach for a subproblem of the problem, and that's very powerful. The solvers that we actually use for exact solving depends also on the client that we work with. Some already have licenses. Some are just happy to go with the choice that we go for. So I cannot give an exact answer to what we do in general, because it really depends on the project a lot.
Well, that makes sense. Yeah.
Yeah.
Hi, Andrea. I just wondered, a bit of a weird question, but did the Raven and the Badger was that just kind of because they're your favourite houses in Harry Potter, or does it have is it something to do with optimization as well? I wasn't sure.
I just saw it as an example because Ravenclaw represents the witty and the smart, and the
Oh,
Hufflepuff are more the hardworking, loyal ones. But I'm happy you you saw
I was going to say, you got it the wrong way round, because the exhaustive search is the hard working, and the cutting things down is the smart. So you got it's the wrong way round.
Yeah, I guess it's a matter of how you view it. Yeah.
Yeah.
I guess one more thing for me, Andrea. If people want to sort of learn more about this and do some more reading or some playing around, do you have any sort of recommendations of sort of books to look at, or libraries, or tools to have a look at?
I think that if you really want to try it out yourself, there's a really good Coursera course that's called Discrete Optimization. It's by Pascal van Hentenrijk, who is a very famous professor in optimization, and he has extremely good videos where he explains different concepts and both heuristics and exact approaches. And they also have very difficult examples for you where you can write your own solving approach and you can submit your solution. So this is if you really want to have either a hands-on experience, and you might also just want to watch the videos. That's really nice. If you want an easier entrance, you might also want to look into so if you're, for instance, not a very experienced programmer, what you can also do is mainly just work with modeling languages. So these are languages where you just have to model your mathematical problem, and everything else on the solver side is done automatically within this tool. So one modeling language that I like a lot is Minisync, and there are also Coursera courses on how to learn those. I think those are the things that I would think of right at the top of my mind. There are probably several other really good resources that you'll find.
There was a course by MIT. They do this thing called MIT Open Courseware. There was a course that they did on some sort of rudimentary. It was like a 1.0 something course, or rudimentary solving these tree problems. Like when they go through the basics, like depth first search and breadth first search and min max and all sorts of the basic algorithms of that sort of thing. And I think there's one called domain reduction as well, where you're reducing problem domains and eliminating branches of the tree like that. But they really go through it's like 12 hours of lectures. Really interesting course on this exact topic. It's a good intro, I think.
Oh, that sounds great. Yeah.
Nice. Yeah, sounds good. Thanks. Okay, brilliant. Well, thanks for your time. That's a really good talk. Really good to hear about that stuff.
Thanks for the invitation. Okay, I hope you have a good day.
thank you.
Thank you. Thanks for your time. Bye.